Now let's talk about effective nuclear charge. The effective nuclear charge is denoted by Z subscript EFF and is defined as the positive charge felt by an electron outside the nucleus. So if you have a nucleus, call this the nucleus, and then let's go outside the nucleus and draw some shells. I'm going to draw 3 of them. So imagine you have an electron on n equals to 1 and another electron on n equals to 3. Now remember that the nucleus has protons and neutrons, so you can imagine that the nucleus is positively charged. Why? Because neutrons are neutral, protons are positive, electrons themselves are negatively charged. Question to you: which of these two electrons will be much attracted to the positive charge? Of course, it's going to be the one that is closest to the nucleus, the one that is on n equals to 1, energy level equals to 1. The one that is farther or farthest from the nucleus will be less attracted to the positive charge. Opposite charges attract. Okay, so the nucleus is positive, is going to attract the negative charges, which is the electrons spinning in their own orbit around the nucleus. Now, there's a problem. Here's the problem. If this is your nucleus again, and you have a bunch of energy levels, so let me draw now. This time I'll exaggerate and put an electron on n equals to 4. So remember how you have an electron on n equals to 3, and then let's assume you have an electron on n equals to 1, and of course you have another on n equals to 2. So these electrons will be attracted differently to the nucleus, which is positive. Electrons are negative, the nucleus is positive. Now by the time the one on n equals to 4, the electron on the 4th energy level, by the time it feels the positive charge strength, the nuclear strength, will have been diluted or reduced by the inner electrons. So the inner electrons will have reduced the positive charge strength or force of attraction by the time that positive charge environment, that positive charge field, that positive charge strength gets to the electron on n equals to 4, which is why we use the word effective nuclear charge. It's going to be reduced. N equals to 4 is not going to feel the full power of the positive charge of the nucleus. Okay? Again, I repeat, the nucleus is positive. The electron on n equals to 4, the green one right here, is not going to feel the complete effect of the positive charge of the nucleus, because the electrons that are before it, that are closer to the nucleus, will have taken out some of those positive charges strength. Okay? So the effective nuclear charge is going to be equal to the atomic number Z, which is basically the protons in the nucleus which are creating the positive charge, minus the number of inner core electrons. What are the inner core electrons? It could be the purple and the red and the red. Those ones, they shield. So these ones, they shield the green outermost electron from the nucleus, so the green outermost electron will feel less nuclear charge. So which is why we subtract. So you take the atomic number minus the number of inner core electrons to get the effective nuclear charge Z subscript EFF. Now let's compare some values here. So here you have Z, which is the atomic number. So all these numbers are atomic numbers of the elements listed to the left. Sodium has atomic number 11, meaning 11 protons, magnesium 12 protons, aluminum 13 protons, silicon 14 protons. And in turn, if they are neutral, it will match the number of electrons, 12 electrons for magnesium, 13 electrons for aluminum, 14 electrons for silicon. Okay, so the ZeFF is taken to be 1 for sodium, 2 for magnesium, 3 for aluminum, 4 for silicon. They match the number of valence electrons in these elements. The core electrons are the ones that are shielding the outermost. So the outermost electrons in sodium is a main group 1 element, is 1. Magnesium is alkali earth metal element, main group 2. And then aluminum, you'll find him in 3A. Silicon, you'll find him under carbon in 4A. So the core electrons are 10 for all of them. Now let's compare. If all of them have preceding 10 electrons before the outermost electrons, who is going to have the biggest radius? We expect that the one that's going to have the biggest radius will be sodium, and the one that's going to have the smallest radius is going to be silicon. And the reason is silicon has more protons in the nucleus than sodium. Now I'll explain it in a different way. All these, sodium, magnesium, aluminum, and silicon, you're looking at sodium, magnesium, aluminum, and silicon. All of them are found in the third. All of them are found in the third period. You see that? They're found in the third period, the third row. So they all have 3 shells. The difference is the number of valence electrons and number of protons in the nucleus, but I'll heavily focus on number of protons. So you have 14 protons, or 14 positive charge in silicon. If I was to draw sodium with the same energy shell, sodium has 11 positive charges, meaning 11 protons. So which one do you think is the strongest nucleus? It has to be the one for silicon compared to that of sodium. Now, if this is stronger, you expect these shells to be pushed inward stronger. The same 3 energy shells will be pushed closer to the nucleus than that of sodium. Okay, because sodium has less nuclear power. We call that effective nuclear charge. So you expect that sodium is going to be bigger, 186 picometers, compared to silicon. Okay, silicon is going to be smaller of this. Much protons in the nucleus in silicon than sodium, pulling in the same number of energy shells which carry the electrons, makes the silicon to be smaller, having the smallest atomic radius of the 4, and therefore the size will be smaller compared to that of sodium. That's the idea. Okay, so the effective nuclear charge increases across the row, what you call the period, with increase in number of protons, meaning with increase in atomic number. So it increases that way. And we just saw an example where you have sodium, I believe, somewhere here. This is magnesium. And then aluminum is here, silicon is here. They are all in the same row. Which row? The third row. So all of them will have 3 energy shells because they're in the third row. N equals to 1, N equals to 2, N equals to 3. That's what dictates. The number of shells dictates the row, the period of the periodic table. However, as you go across the periodic table like this, the nucleus is increasing number of protons. You are increasing the positive charge. So the nucleus becomes more positive. You know, the shells contain electrons, so the electrons will be pulled inward towards the nucleus more in silicon compared to sodium. Silicon has 14 protons, sodium has 11 protons. So you can say sodium has 11 positives, silicon would be taken to have 14 positives. So that's why silicon is going to be smaller compared to sodium, which is going to be bigger. That's the idea. Now the trend in a group, if you compare sodium and potassium, for example, let's compare sodium and potassium. Potassium should be just below the sodium. What happens to effective nuclear charge in this case? So we see that sodium has 11 protons, but potassium has how many? Let's look at the periodic table. Oops, where's my potassium? Potassium is right here. Potassium has 19 protons. Potassium has 19 protons. So this has 11 positives. This has 19 positives in the nuclear charge. And so you'll expect that the effective nuclear charge will increase as you go down a group in the periodic table. The nuclear power will be more in potassium than in sodium because potassium has more positive charges, 19 protons. Okay. Let's talk about the atomic radius in terms of intramolecular bonds. So if you have a copper and a copper, the bond in between there is called metallic bond because you're looking at a metal and a metal. Okay, but if you have a hydrogen and a hydrogen, this bond is formed by sharing electrons. We call this covalent bond. We talked about this in earlier chapters. And so if the sharing of electrons, if you bring hydrogen 1 very close to hydrogen 2, there's going to be an overlap. There's going to be an overlap where they're overlapping. That's where we're making a bond. And that is where electrons reside, which are shared to make the bond, covalent bond, shared electrons that make a bond. They make the covalent bond between hydrogen and hydrogen. So now, because there is overlap, you expect the radius here to be smaller than in the metallic bond. Here, there's an overlap, and therefore there is reduced internuclei distance. That's what we call it, reduced internuclei, the distance between nucleus, the two nucleuses here and here, is reduced. So we have an overlap that causes reduced internuclear distance. So you expect the covalent radius to be shorter than the metallic one. Why? In metallic, there's no sharing. The atoms will just barely touch. So you have maximum radius between the two nucleuses. So we can conclude that the covalent radius is always less than the metallic bond radius. Okay, so covalent bond radius is always less than the metallic bond radius because there is an overlap. Right here, there is an overlap of the atomic spheres. So atomic radius is shorter in covalent bonds than in metallic bonds. That's the conclusion. Now let us look at atomic radii representation in the periodic table, just a visual look of it. We all know that the metals are usually found to the left. Okay, look at these guys except hydrogens. Let's look at this. and now focus on each period. I know that these are metals, and you know that those are metals. See, lithium atomic radii is bigger than that of fluorine. Now, there are a few reasons for this. Now, if you look at lithium with atomic number 3, he has 3 protons and he's going to have 3 electrons for sure. So it's going to go 1s2, 2s1. Now compare that to fluorine. Fluorine has atomic number 9, which means it's going to have 9 protons, 9 electrons. Electronic configuration is 1s2, 2s2, 2p, 2p5. Now, the main thing here is for you to see that both of them are in the second period, lithium and fluorine. I know that because of the outermost shell, n equals to 2 for both of them, n equals to 2. Meaning you have an atom that has 2 energy shells, there and there. Here n is 1, here n is 2. So imagine that this is that of lithium with 3 protons in there, okay? In fact, you can say 3 positives. And then look at the nucleus of fluorine. I know I've already explained this before, but it doesn't harm to repeat. Look at the nucleus of fluorine. Fluorine has 9 protons, meaning he has 9 positives. Which nucleus is stronger? Of course, the effective nuclear charge of fluorine is going to be stronger because he has more positives, attracting the same number of energy shells. So you expect the energy shells in fluorine to be pulled closer to the nucleus, energy shells in lithium, and that inward compression is causing the fluorine to be smaller compared to lithium. And it will be the same thing if you compare sodium to chlorine or potassium to bromine or any other elements in that line. So atomic radius increases from right to left, okay? Or it's going to decrease, if you like, it's going to decrease from left to right. Why? Because of increase in number of protons pulling the same number of energy shells. Okay, so that's the trend here. All right, so this is just a graph, visual graph of showing how things are going. I've explained how lithium is going to be smaller than fluorine. You can see the trend of other elements in between. In between lithium and fluorine, you have other elements. And so here is lithium and here is fluorine. You have these other elements right here, these ones. So the atomic radii will generally also decrease. As you can see, the drop. And the same applies if you are to compare sodium and chlorine. You have other elements in between. Sodium is right here, chlorine is right here, and those other elements generally have a drop in their atomic radius, and so on and so on. Okay. Now let's work on an example. Example 8.2. Referring to a periodic table, arrange the following atoms in order of increasing atomic radius: phosphorus, silicon, and nitrogen. So generally, our periodic table will look like this. Okay. I believe generally carbon is here, nitrogen is here, oxygen, fluorine, sulfur is here, phosphorus is here, silicon should be below carbon, nitrogen, I've shown it. And I believe I'm accurate with this, because if you look here, you have carbon, nitrogen, oxygen, phosphorus, fluorine, sorry. And then you have silicon, phosphorus, and sulfur. So yeah, my estimation is correct. So my focus is going to be on the silicon, the nitrogen, and the phosphorus. Now, if you're going down a group, you're increasing number of shells. For example, I know that carbon is going to be in period 2, phosphorus is going to be in period 3 in our periodic table. Let me count 1, 2, 3. Phosphorus is in period 3. So you're increasing the number of shells. So I expect that silicon and phosphorus will have 3 shells. They're found in group 3, if that is silicon. And then phosphorus, I know it's supposed to be a little bit smaller. Okay. But nitrogen is going to have 2 shells outside the nucleus. So if that's the nucleus, I only have 2 shells. There's no brainer. If I'm talking about increasing atomic radius, nitrogen should be the smallest with 2 shells. Now, in terms of silicon and phosphorus, we say that as you go to the right, the number of protons are increasing. Actually, I think silicon has an atomic number 14, meaning 14 protons. In the nucleus, phosphorus has atomic number 15, meaning 15 protons in the nucleus, pulling 3 shells and 14 protons, pulling in 3 shells with the electrons in them. So I expect that the atomic radius in phosphorus will be less than that of silicon, because he has a stronger nucleus that pull the electrons in the shells closer to the nucleus, because you have more effective nuclear charge. So I'll go NPSI. Nitrogen is less than phosphorus. Phosphorus is less than silicon. That is the trend. Exactly. That's the order. So we judged nitrogen and the rest, knowing that nitrogen has 2 shells. The rest have 3 shells. But silicon here will have the biggest because he has 14 protons compared to phosphorus, which has 15 protons. Remember, the lower the number of shells, okay, the lower the atomic radius. You have few circles around the nucleus, the radius will be small. So that is the reasoning. Let us now do a comparison of atomic radius and ionic radius. All right, so now looking at some atoms and their ions, we start with lithium. Lithium here has atomic number 3, meaning 3 protons. If he has 3 protons, I can judge that he has 3 electrons. Now, I know that lithium is a metal, therefore, he loses electrons when he is reacting. And he is in the main group 1 of the periodic table. Just to slice a periodic table here, is in main group 1, lithium is somewhere here. So you react by losing 1 electron. So using the example of lithium, I know that lithium is going to form Li+, meaning you lost an electron, which is this electron right here, lost. So you get a positively charged species we call a cation. Lithium before was an atom. So you're comparing here, the atomic radius of lithium seems to be higher than the atomic radius of lithium cation. What caused the drop? Here is the illustration. You have 3 protons. Remember, the number of protons are not changing. And then lithium goes 1s2, 2s1, right? So there's 2 electrons here in n equals to 1. The other electron will be where n equals to 2. Why? N equals to 1 carries a maximum of 2 electrons. Now, if you're going from here and you're losing an electron, what that means is that the number of shells will decrease. So n equals to 1 will stay. N equals to 2 lacks an electron that was lost. This electron here was lost. So you see, there is what we call a decrease in number of shells. And visually you can tell that the radius here, we call this Li plus, so we're going to call that ionic radii, because Li plus is an ion, specifically a cation. So you see the ionic radius is smaller than the atomic radius. You remember the radius goes half the circle because of loss of one shell. That explains the drop. And the same explanation will apply to the rest of the elements. K going to K plus, rubidium going to rubidium plus, cesium going to cesium plus. So that is why there's a drop whenever you're considering metals forming their ions. Now, how about the nonmetals? What happens? It seems that these are the atoms down here, and these are the ions. Specifically, we call them anions because they have a negative charge. It seems like the radius increases. For metals, there was a drop. For nonmetals, there's an increase. What is the reason? Let's focus on the atom of fluorine. Fluorine has atomic number 9. Okay, so let me deal with it here. Fluorine has atomic number 9, so 9 protons. That means he has 9 electrons. So we have 1s2, 2s2, and then 2p5. Now, when the fluorine reacts, he's a nonmetal. He only needs 1 electron to fill up the p. So he reacts by gaining. Nonmetals react by gaining to give you a fluoride. Here, you had 9 electrons. Here, you're going to have 10 electrons because the fluoride will be now 1s2, 2s2, 2p6. Now, you're going to have the same number of shells. Okay. Really, I was drawing the atom here, but let me draw it down here. You're going to have the same number of shells. However, so I'll call this F minus and this the atom. So that's the atom and this is the anion. So you have the same number of shells because I see that I'm going up to the second shell from the atom, in the atom and in the anion. Only that this guy will have, let me see, we said we have 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And now 1, 2, 3, 4, 5, 6, 7, 8, we have 10. So this is gonna have more electrons, meaning more negative charges. And since you have more negative charges, the nucleus here is gonna be kind of diluted or overwhelmed. So we expect the radius here to increase. Okay, in fact, if you have more electrons, there's more repulsion out there. So electrons will be distancing from each other. The ion structure will expand. So here you have 9 electrons, here you have 10 electrons. More electrons mean repulsion out there in the shells, and also you have more negatives than the protons because the number of protons stayed the same. You still have 9p and 9p. It did not change. What changed was an increase in number of electrons. So since you have more electrons in the fluoride, okay, let me just say F minus, then you expect the nucleus to share its effective nuclear charge with more electrons, and therefore the radius will be bigger. Here you have 9 protons attracting 9 electrons. Here you have 9 protons attracting 10 electrons. Less effective nuclear charge. Atomic radius will increase. And it's the same story from bromine to bromide or chlorine to chloride. That's the comparison. So generally, ions of metals have are smaller. They have less atomic radius compared to the atoms themselves, and the atoms of nonmetals have less atomic radius compared to their ions, their anions. Now let us compare a reaction between a metal and a nonmetal. We know that lithium has one valence electron, so it's helium 2s1. On the other hand, we know that fluorine has 7 valence electrons, which is going to be helium 2s2 2p5. Okay. It's easier for lithium to lose that electron than to gain 7 more electrons to fill up the second shell. And it's easier for fluorine to gain 1 more to get 8 valence electrons, same as neon. Okay, so what will happen here is that the lithium is supposed to lose the 1 electron to give you lithium ion. Okay, so let me do it this way. Let me put the lithium with this newly formed electronic configuration, Li+, there's no more 2s1 is gone. He lost 1 electron to who? Suppose this is the most outside energy shell. Lithium loses that 1 electron to fluorine. Suppose that this is the most outermost shell of fluorine. He loses it there to pair up probably with 1 electron that was out there. Remember, you have 7 valence electrons to pair them up. So as lithium loses it, it loses this energy shell entirely, so it becomes smaller. But as fluorine gains that extra electron, there's more repulsion out there, so fluoride is bigger than fluorine. So you can see this one was bigger, this is the before, but now it's smaller. And this is smaller, but now it's going to be bigger. So that is what I just explained here, comparing the metals and nonmetals before and after they lose or gain an electron. So in conclusion, cations, the positively charged ions, will always have smaller atomic radius than the atom from which it's formed. And then anions, the negatively charged ions, will always have larger radius or radii than the atom from which it was formed. So lithium plus will be smaller than Li, while F minus will be greater than F. That's the relationship. Okay, so here you're looking at the radii or the radiuses in picometers. PM is not the PM of time, is the picometers of ions of familiar elements. So now remember how we said that ions of metals are smaller than the atoms of those metals, and anions of nonmetals are bigger than the atoms of those anions that form those anions. So you're looking at a visual representation of these ions, cations and anions. Remember, cations are the positively charged ones, and they'll be seen somewhere here. And then the anions will generally be on the left side. So again, I'll remind you that nonmetals, they will always form anions, and the metals will form cations. And you can see that the anions are really bigger. They are bigger than their counterpart, the cations. All because they gain electrons, and there will be electron repulsion energy shells outside the nucleus, and the atom is going to be bigger. And the other reason is because now you have the same number of protons as in their atoms, but attracting so many more electrons. So you expect the atomic radius, which is the distance halfway the sphere, is going to be bigger here compared to the distance, for example, in a metal cation. So this table is just a summary, visually comparing the sizes of the cations as compared to the anions. Let's look at an example, example 8.3. For each of the following pairs, indicate which one of the two species is bigger. Now, I'm looking at nitrogen and I'm looking at fluorine. Now, let me just visually draw. This is my nucleus of nitrogen. Nitrogen, I believe, is supposed to be in period 2. Let me pull up a periodic table. So nitrogen is right here. He is in period 2. He does not increase the number of shells when he gets the new electrons. He keeps the shells as 2. Fluorine is in the same period 2. And even when he gained an electron, he keeps the same 2 shells. The only difference is that the number of protons here will be different. Nitrogen has atomic number of 7. So he has 7 protons, or rather 7 positives. Fluorine has 9 protons, atomic number of 9, Z equals to 9 here, while Z here is 7. So he keeps the 9 positives. So which of these do you think will be larger? Definitely is going to be the one that has less protons. And that, my friend, happens to be nitrogen with 7 protons. All right, so you have N having 7 protons, you have F having 9 protons, but you have the number of shells equals to 2. This one has more effective nuclear charge, which is the force of the nucleus to attract the electrons, outermost shells towards him, pulling the shells towards the nucleus. So these fluorines gonna be smaller. Now let's consider the number of electrons. To justify this, nitrogen itself has 7 electrons. He gains 3 more to give you the nitride. Okay? This gives you 10 electrons. Fluorine itself usually has 9 electrons. He gains 1 more electron to give you 10 electrons to give you the fluoride. Now let's come up here. You have the nitride carrying 7 protons and now 10 electrons. You have the fluoride F minus carrying 9 protons and still having 10 electrons outside. And both these two, they have 2 energy shells. Take the protons to be the force of attraction of the nucleus. So who is going to strain here? It's almost a 1-to-1 ratio between the 9 protons and 10 electrons in the fluoride. So there's a stronger attraction here. This is another way to look at it. The effective nuclear charge of fluoride is bigger than effective nuclear charge of the nitride, and they are all attracting 10 electrons towards the nucleus. So I would expect that since the fluoride is stronger, its ionic size, let's pretend that's the ion, its ionic size is going to be smaller. So I expect the ionic radius of the nitride to be bigger than the ionic radius of the fluoride. So I would say nitride is bigger than the fluoride. Just to remind you, species that have the same number of electrons are always called isoelectronic. The nitride and the fluoride are isoelectronic because they both contain 10 electrons. Let's work on part B. For part B, we need to decide between Mg2 plus versus Ca2 plus, which one is larger? Now, first things first, magnesium has atomic number of 12, I believe. Let's confirm. Yeah, magnesium has atomic number 12. So magnesium has 12 protons, meaning it's going to have 12 electrons. We know also that magnesium is on the left, so it's a metal. He has to react by losing. So magnesium in main group 2 has to lose 2 electrons to give you magnesium 2 plus cation. Now we are keeping the number of protons. We are keeping the number of protons, only that the number of electrons will change. So looking at the number of electrons here, there are 12 electrons, but you lost now, you have 10 electrons. The electronic configuration here is 1s2, 2s2, 2p6, like that of neon. But I want you to focus on the complete electronic configuration. Now, if you're talking about calcium, calcium has atomic number Z, 20 protons. By inference, those will be 20 electrons. And his metals in main group 2, you will see it in the second group right here, alkali add metal. So he reacts by losing 2 electrons like magnesium to give you Ca2 plus. The number of protons will stay the same. Number of electrons will change to 18 electrons. The electronic configuration will be 1s2, 2s2, 2p6, 3s2, 3p6. You see how you're going to the third shell, but this one stopped at the second shell? Here will not use the number of protons. The one that has more circles or more energy levels will definitely going to be bigger. So I expect that Ca2 plus will be bigger than Mg2 plus, which has only 2 energy levels. So that's my reasoning for this. The atom size will dictate the ion size in this case because they are in different periods. This one has n equals to 3, the Ca2 plus, but magnesium has n equals to 2, the magnesium cation, Mg2 plus. The one with more circles will be evidently bigger because this magnesium here will only have 2 energy levels, it's smaller. Now let's compare ion 2 plus and ion 3 plus. Let's see, we are comparing ion 2 plus and ion 3 plus. Now, just based on the charges, you can tell that ion 3 plus, or rather ion 3, is one electron less than ion 2. The greater the positive charge, the less electrons present. Now, the one that's going to have fewer electrons on the outside of the nucleus is going to be having less electrons to be attracted by the nucleus, so there will be greater effective nuclear charge. This one is going to be 1 electron more to be attracted by the nucleus. This is 1 electron less to be attracted by the nucleus. So I expect that ion 2 plus is going to be bigger than ion 3 plus because ion 2 plus has 1 electron more to be attracted, while this one has 1 electron less to be attracted. Remember, both of them have the same number of protons. So they have the same number of protons. The atomic number of Fe is 26. So both of them have the same number of protons, 26. So the 26 protons attracting the less number of electrons will be more effective, making the atomic radius to reduce in ion 3 plus. Just as a note, out of the 117 elements, 2 of them are liquids at room temperature, 25 degrees. Bromine is an nonmetal
that happens to be a liquid. Chlorine, fluorine, those ones are usually gases. Iodine is a solid. Mercury is a metal that is also a liquid. It's the only liquid metal. Now the graph, don't worry about, have to talk about that in a different chapter when time comes. The graph below compares the melting point in relation to the atomic number of elements, and it seems to reduce from lithium going downwards when considering the same elements in group 1. And this probably is due to the size increase. Increase in size probably is decreasing the melting point. So as the atomic number increases, the melting point will also decrease, but in a curve way.